Hello, and welcome back to another episode of South Pole, the podcast that explores everything Antarctica. I am your host, Clark Marchese, and today we are talking about cold dirt, Antarctic forests, permafrost thaw, Martian climate change, space exploration, and the world's largest desert. Okay, it is Dirt Day, everyone. Finally, we made it. Today, we're talking all about dirt and permafrost in the Antarctic. The research questions that scientists are asking about it, how the dirt is changing, how old the dirt is, what the dirt can tell us about the past. Are we getting more dirt soon? Is that a good thing or bad thing? And we will find out all about that in just a moment. Today's guest is Dr. Joe Levy, an associate professor of Earth and Environmental Geosciences at Colgate University. Dr. Levy is a geomorphologist and a planetary scientist with a passion for studying permafrost landscapes on Earth and beyond. His research spans both terrestrial and planetary science, focusing on the surface processes and geological-ecological interactions. He has led significant research initiatives, including fieldwork in Antarctica and investigations into glaciers on Mars. He is also part of a research laboratory called the Cold Dirt Lab, which we will learn more about today. And yeah, we have a lot to cover and a lot of vocabulary words in this episode. So buckle in and I will see you on the other side. All right. Hello, we are recording. Well, the first question I have for you is if you could just introduce yourself and tell us a bit about your research.
Sure. I'm Joe Levy. I'm an associate professor of Earth and Environmental Geosciences at Colgate University in beautiful central New York State. And I'm in the business of figuring out how soil and water and ice and salt and life all interact in cold landscapes, from Antarctica to Mars and anywhere there's cold dirt in between.
Amazing. We are definitely going to be talking about Antarctica, and we're going to be talking a little bit about Mars too. But one question I like to ask on the top of the show is, I don't think you've been to Mars, but it's possible you've been to Antarctica. So if you have, can you tell us about some of the research projects that took you down there?
Sure. Yeah, I've been going to Antarctica since 2004. I started as a graduate student and I've been back probably 13, 14 times at this point, going through all the stages of an academic life cycle, so postdoc and now as a faculty member. And yeah, I've worked on a wide variety of things, mostly with the United States Antarctic program, a little bit with colleagues at Antarctica and New Zealand, doing everything from mapping permafrost landscapes with high-resolution laser scanners to using delta deposits left behind by paleolakes during the last ice age to try and reconstruct ice sheets. So kind of a little bit of everything. But what unifies all these projects is working in the McMurdo Dry Valleys of Antarctica, which are this tiny corner of the continent that's not completely covered by ice sheets. And so there's exposed rock, there's exposed soil. And so right now I'm finishing a 5-year project with the National Science Foundation, trying to figure out how soil is born in this cold desert. How do you take a little bit of snow melt every summer and have that water percolate into the ground and form these sort of underground streams called water tracks? And is that a place where soil is being born in the Antarctic continent?
Okay, I'm taking notes because there's probably some vocabulary words that we will need to work through. But first, let me just ask you, what made you interested to study soil and sediments?
I've always loved to hike and be outside. And when I discovered I could be paid to do that for a living, it seemed great. But actually, my super nerd origin story goes back to college and sitting in a biology class, a chemistry class, and a geology class, the last one I took totally on a lark. And all of them began the very first day with, 4.5 billion years ago, the Earth accreted out of dust and ice, all blobbing together. And I thought, whoa, like that's the beginning. That's where life, as we know it, that's where the elements that make up life, that's where everything started. So maybe I should become a geoscientist because that's where all this stuff began. And since then, I've become one.
One word that I've seen associated with your work is geomorphologist. Do you identify as a geomorphologist?
Yeah, I mean, I wear a lot of hats, but geomorphologist is great. That's someone who studies the earth, and the morphology of the geo, so the shape of the earth. And it's a term I really like because it means I study landscapes and how they evolve, what they're made out of. and particularly how climate affects them. And so, the surface of the Earth is awesome because it's the Earth, but it's in contact with the atmosphere. It's in contact with water and the water cycle. And so if you're interested in climate change, if you're interested in water resources, everything's going on at the surface of the planet. And that's where geomorphologists spend most of their time, is studying those interactions between the solid Earth, the liquid Earth, the gaseous Earth, and for me, the icy Earth.
Awesome. You work also with an organization called the Cold Dirt Lab. Is this the kind of work that you do there?
Oh, yeah. So the Cold Dirt Lab is just the name for my lab group. I've moved from multiple institutions over the years. It's nice to have the Cold Dirt Lab group and alumni and colleagues who can always kind of move with me. So we're interested in how climate interacts with landscapes on timescales from seasons to years to millions of years. And so really anywhere in the solar system that ice is part of the landscape, there's someone in the Cold Dirt Lab doing some work. And I think we're all really keen on ice in the landscape because where you have ice, you have melting or sublimation, right? When ice is fritters away into gas. And so what it means is those landscapes with ice in them change really quickly. So other geologists might, look at a landscape that changes, a mountain range that changes over millions of years. But for me, it could be weeks, it could be years. So maybe I'm just not very patient. But I study quick changing landscapes in the Cold Dirt Lab. And so right now, the Cold Dirt Lab is at Colgate University, and I work with a team of outstanding undergraduate researchers on these projects.
Okay, there's a lot to unpack, and I'm taking even more notes, so we'll circle back to a couple of things you said so far. But one phrase that stuck in my mind was about soil being born. What does it mean for soil to be born?
So soil is a living thing. It's composed of sand grains and mineral grains, but also organic matter, also the water in the soil, the gases in the soil. And so, when you go outside and dig a hole, there's worms, there's beetles, all these things you encounter. There's no doubt that soil is alive. But in Antarctica, it's this Mars-like cold polar desert. It is super important that people understand that Antarctica is a cold desert. That's what really makes it special. It's below freezing most of the year. It's particularly way below freezing most of the year. And it's all sediment grains that have been dropped off by glaciers and ice sheets grinding over the landscape for the last several million years. So basically, it looks like a gravel pile. It looks like sand and dust kind of all mixed together, like there wouldn't be any life in it at all. And in the McMurdo Dry Valleys, where I do most of my work, there is this tiny fragile ecosystem that has Antarctic forests or microbial mats like algae that's growing on the damp soil or in the little seasonal stream channels. And then the lions and tigers of the Dry Valleys, my colleague Byron Adams calls them that, are nematodes and tardigrades and organisms that 100 of them could fit on your pinky nail. So tiny, tiny creatures. And so the question here is how do you go from sand and dust and gravel to something that looks like a living, breathing soil? And how does organic matter build up in that soil? And right now, in most places in Antarctica, that's not happening. But as you look to the future, as the world warms up, as Antarctic permafrost thaws, those soils are going to be born. And so we're going to get organic matter mixed in. We're going to get organisms living in there. And so what we really want to know is there a place we can go now to look for a preview of what's going to happen across the whole continent as it deglaciates? And that spot for previews now are these Antarctic wetlands that I study, the water tracks, because they're the places that today have water and have seasonal melting in summer and are beginning to go from gravel to something that's smelly and full of organisms and really quite wonderful.
Okay, and maybe before we go any further, let me ask you about the term permafrost itself. In my understanding, that just means like frozen soil. Is there anything more technical to the definition than that?
Great question. There's a reason I chose Cold Dirt as the name of the lab, right? It's like a real simple explanation. But so permafrost, strictly speaking, is soil that has remained frozen. That's an important thing. So it never thaws for at least 2 years. That's sort of the official, sparkling wine, champagne dividing line there. But most permafrost has been frozen for much, much longer. So all the permafrost in Antarctica has been frozen since at least the last ice age, and probably for millions of years actually prior to that. But that doesn't mean that no soil thaws there. So the very top of the soil, when I'm walking around in the dry valleys in summer there, so like December, January, the upper part of the soil has thawed, it has melted, and that's called the active layer. That's the seasonally frozen and unfrozen part of the ground.
Is there like a standard depth where the active layer starts and stops, or does it just sort of depend on how much has thawed in a given area?
it varies across the landscape. And one thing we spend a lot of time doing is measuring the active layer thickness, because that tells you, is the soil thawing more? Is that permafrost melting from the top down? And so, you'll see us going out across the landscape, but, it looks like minesweepers or something. We have these big, long T-probes, a big steel rod, a little handle on top. And basically, it's like we're probing for, I don't know, whatever, water, gold, you name it. Or maybe it looks kind of like the big dynamite plungers from black and white movies, where we're poking the probe in the ground, because that way, when it hits something solid, that something solid is frozen ground, is the ice. And so we can then measure that depth. And so, of course, in the water tracks, in these wet soils, in these wetlands, these Antarctic marshes, it's thawing really deeply, right? Wet soil thaws really deep. Whereas the dry soils in the dry valleys, which are most of the soils, are like an insulator. They're like a pot holder. And so mostly the Antarctic permafrost is really stable. It's been resisting warming. It's been resisting thawing. For the longest time, we've really thought that it's not going anywhere, although that is maybe changing.
Okay, we'll discuss that, because you touched on something that I've heard from a number of scientists who work in Antarctica, whether they study the oceans or a species that lives there. Basically, they're telling me that the Antarctic climate, the ecosystem, what have you, it used to be extremely stable, and now it seems like it's not necessarily as stable as it used to be. So I want to check my understanding based off of what you said. I'm hearing that with increased thawing, more soil will be born. But I also know that with ice in Antarctica, for example, there's some level to which it's supposed to melt and refreeze with the change of the seasons. And that's part of this stable system, right? So my question is, in the era of global warming, are we seeing a trend of more thawing of the permafrost than there should be to maintain that stable system?
Yeah, so folks have been looking for this smoking gun of climate change in the permafrost record in Antarctica a while now. And so people have been probing the active layer and saying, okay, is the active layer thickening? Are we getting deeper and deeper thaw every summer? And, in the early 2000s into the 20-teens, it was kind of like, no, like they're really consistent, they're really consistent, they're really consistent. And so folks measured the permafrost temperature underneath that active layer. They would drill down in boreholes and say, okay, is the permafrost warming up? Because that would be another sign that it's still below freezing, but it's warming up. And, maybe one or two places it was beginning to look like that. But really, in the last sort of 5 or 10 years, one thing we've been seeing is that the amount of summertime heat that's available has been increasing. So the summers are beginning warmer, the peak temperatures are beginning warmer. So that's kind of potentially thawing the permafrost from above. It's expanding those active layers. But one thing we started looking at just this past year that was really interesting is we have this 30-year record of weather station records from the McMurdo Dry Valleys, a long-term ecological research group, emphasis on long-term. And one thing I was really curious about is what's going on in winter, right? No one is there in winter, so we have to rely on our instruments. And if you look over the last 30 years of winters have actually been warming up in the dry valleys. And now we're still talking like minus 20, minus 30, minus 40 degrees Celsius, but they've been getting warmer and warmer and warmer. And what that means is the permafrost is not cooling off as much as it used to. And so I'm beginning to wonder if this permafrost is actually in a vise, like where it's being squeezed from both sides. It's thawing more in summer, it's freezing less in winter. And so if you project these calculations forward for what's going to happen to the permafrost and just put that straight line into the future, there are patches of Antarctica that could become permafrost free as early as the early 2100s. And that's way earlier than anyone thought. Again, everyone had this kind of vision that Antarctica was insulated or isolated from global climate systems, and it's not. It's coming for the ice too.
Then I have a series of questions about the consequences of that thawing. Let me first ask you how the thaw affects the soil properties itself, such as, I don't know, salinity, oxygen levels, maybe. And then also how any of those changes might affect the soil biota, anything living in the soil in any way.
Oh, great question. Yeah. So as the soils warm, they become more habitable, more hospitable to life. There are corners of the dry valleys that are actually too cold and too dry for anything to live. So as the soils warm up, it's possible for microbes to colonize them, for these microbial mats to spread. The microbial mats really need water, right? I mean, they're a plant-like organism. And so the wetter the soils they get, the more they thaw, the more that ground ice kind of can wick up like a wet sponge that you would use to keep a plant going if you were transplanting it somewhere. That's going to be good for primary producers. That's going to be good for the Antarctic forests that are going to be pulling carbon dioxide out of the air and putting it into the soil. Many of the microbes and larger organisms that live in the soil like warmer temperatures too. Some of them don't. They're of course adapted to live in Antarctica. But if you just add water, these things start metabolizing. They start eating the microbes. So really, warmer, wetter soils in Antarctica will probably mean more clement conditions, more critters living in the soil. That's the point where I say I'm a geomorphologist, not a real biologist, because I call them critters. From their perspective, warming conditions are probably better if you want to multiply and thrive and really kind of inhabit the soil and create a thriving soil ecosystem. Right now, the soils there are limited by water and by temperature. But as the soils get wetter, what you're going to notice is that you'll start flushing out all of the salts that are in the soil. So right now, the Antarctic desert is unusual because it's cold, because it's dry, but also because it's extremely salty. It's been so cold and so dry there for the last, in some cases, 3 million years, some cases 8 million years, that salts have built up in the soils. And so as those salts get flushed out down through these underground streams, these sort of water tracks into the wetlands, sometimes it's like pickle juice. I mean, it's like actually too salty for organisms to live. So there's this real competition between the soils getting warmer, the soils getting wetter, and then also the soils getting saltier. And so the real tug of war we're trying to figure out now is which is going to win. Is the soil eventually going to sort of flush itself out of all these salts and become something more like Arctic soils, which are, have grasses growing in them, and you could have mastodons walking across the tundra, during the last ice age, or are we talking basically that this is going to be a salt flat and a salt lake kind of situation, and it'll be very hard for organisms to live there.
Okay, interesting. So there may be a bit of scrambling of which species can live where, if any, and if they can, which species thrive, which new ones get introduced, how they interact with the ones that are already there. So I guess we have to keep an eye on that. But I'm also curious, will the washing away of these minerals in the soil, will that be at a large enough scale to actually affect the surrounding ocean water too? Because we know that marine life is adapted to current conditions and might be affected by a change like that if it's at a large enough scale.
Oh, sure. So the interesting thing about this, again, is that, the dry valleys are a small part of Antarctica, but they're connected to the Southern Ocean. They're connected to all of Antarctica. And so some really neat work that my colleague Barry Lyons has been doing has been looking at how iron from the soils and is washed out to sea and actually could fertilize offshore organisms, so plankton living in the ocean. And so one thing that makes Antarctica interesting from a geologist's perspective is that it's a place where there's almost no chemical weathering. So if you've had an earth science class, most people think back to like third grade, and they're like, oh, physical weathering, that's when rocks break down into little pieces because you hit them, like with glaciers or other rocks. Chemical weathering is when they dissolve and chemically change. And for years, people said, oh, there's no chemical weathering in Antarctica. It's too cold, it's too dry. And now we're seeing actually that it's happening everywhere, particularly in these Antarctic wetlands. And that's how that iron is getting leached out of the soil and washed out to sea. So there is a real potential for more export of iron and other nutrients into the Southern Ocean, which are otherwise a pretty nutrient poor place. And that's going to mean more plankton living in those waters.
Okay, so as far as the plankton are concerned, they are currently fulfilling their given role in relation to their species-rich ecosystem. So if there's a change, things could get shifted around. But when you mention that when soil thaws, organisms may colonize a new area, species colonization in the past has caused a lot of problems. Dr. Richard Phillips mentioned to us in our third episode that even sailors bringing mice to Antarctica accidentally in the ship cargo had some major consequences for Antarctic wildlife. But if these new organisms are going to be colonizing an area that was previously inhospitable, do you foresee any negative implications, or is that sort of just a cool science fact that will soon start to happen?
Yeah, I mean, so right now the dry valleys are home to organisms that have evolved over millions of years to this cold, dry environment. They've survived ice age after ice age. They really figured out how to survive. And they're a wonderful model ecosystem for studying how organisms adapt to change over time, but also just how, like, fundamentally how an ecosystem is structured. The same way I said, like, it's hard to make a living in Antarctica and to survive there, and that's why I like it. It's all very deliberate. You can really see the connections between the organisms that live there today. And so we actually do a lot of work to try and keep outside organisms from arriving in Antarctica and kind of taking advantage of warmer or wetter conditions. So there's real serious biosecurity to prevent that kind of contamination. But on the flip side, change is happening, right? And so, I think what we're going to see, the long-term feature is the greening of Antarctica and the greening of Antarctic soils. And so organisms that don't live there today are eventually going to arrive. They're going to live in these soils. They're going to grow. And I think that's another important kind of lesson for, like, what's that going to do for carbon in the atmosphere? Are we actually going to have a carbon sink in Antarctic soils as they bulk up and become more Arctic-like? How much? Is it enough to matter? We really don't know. We're just in the beginning of trying to figure that out because there's a whole continent's worth of soil underneath the ice that is going to start playing in global systems. And outside organisms are going to do that. The organisms that live there today really aren't up to that task. They're too adapted to the cold and the dry. But when we start seeing, someday grasses in Antarctica, it was described by the earliest explorers as a great place to grow potatoes. We'll see.
Okay, I think I have more follow-up questions in this conversation than I might have ever had on any other episode, but I do have a couple more.
I'm glad you like dirt too.
It's so much fun. You mentioned a term called Antarctic forests. I'm wondering, is that just a word we just use to describe like the microorganisms in the soil, or is that like projecting into the future where there actually will be forests in Antarctica like we understand forests today?
Oh, I think I'm actually probably the only one who calls these microbial mats Antarctic forests. And you're so used to working on, barren, rocky, gravelly landscapes. When you encounter one of these things, it's like walking into a forest. It's just teeming with microbial life. My question was like, why is it right there? What makes this place special? And how can that environment expand?
Got it. Then I'm wondering, you mentioned that maybe we could see the soil and the growth from it become a carbon sink, but isn't there also a concern that thawing could contribute a climate feedback loop in a way that intensifies the amount of carbon that's trapped in the atmosphere?
Yeah, so in most places, permafrost thaw is a real problem. It has sort of the local problem that if you have ice in the ground and that ice thaws, then it destabilizes the ground surface. And if you have infrastructure or houses or power lines, it wreaks havoc with those. There's also the climate feedback problem with thawing permafrost. So especially in the Arctic, permafrost is full of methane gas. And when that permafrost thaws, that methane is released to the atmosphere. That's a powerful greenhouse gas. And so there's actually a positive feedback loop where thawing leads to methane release leads to more warming leads to more thaw, which leads to more methane release. So this has been called the permafrost carbon bomb, and it should keep people awake at night. It's a potential really fast feedback in the climate system. Antarctic permafrost is not really part of either of those two problems. First of all, there's not a lot of people living there. And so, certainly the bases are worried about permafrost thaw and settling. And there's a lot of infrastructure around McMurdo Station and Scott Base and all the bases. But it's not like whole communities living in the Arctic. And then also, because Antarctica has been covered by ice sheets for the last 34 million years, there's really not much organic matter in the soils at all there, as we can tell. Really, it's coming in from above now. That's what I mean when I talk about the birth of Antarctic soil is sort of a top-down growth of carbon in the soil. So as that permafrost thaws, it's not releasing carbon to the atmosphere in any place we've looked. Really, what it's doing is starting to build up that organic matter. And so it's taking carbon out of the atmosphere. It's turning it into microbial mats. And then that's building up in the soil because it's a real short growing season, right? These organisms can grow in December, January, into February, and then everything freezes up, so nothing can eat them. And so over time, that organic matter can start to build up. So it probably is a carbon sink, and if you deglaciated all of Antarctica, you would have a landmass the size of kind of the U.S. and Canada put together. Some of it's below sea level, but some of it is just waiting to become soil. And, I think that's not a silver bullet. I don't think that's like, the solution to climate change is just to remove all the ice from Antarctica. That is not the case. That's a lot of sea level rise to contend with. But I think what we really have to do is think about Antarctica in a post-glacial world. What's the next step? How does Antarctica actually fit into that? And Antarctica's soils are going to be a big part of that story because in the same way, I look at my window in central New York and 20,000 years ago, we were under 2 miles of ice sheet. So all the soil that's out there today is new. It formed in the last 20,000 years. And right now it's farm fields. It's full of carbon and it plays a role in global climate systems and global chemistry. So we should be doing the same thing for Antarctica. We should be thinking about what role is it going to play after the ice.
After the ice. That's kind of ominous. Oh gosh. Well, I didn't understand that there was so much methane in the permafrost, mostly in the Arctic, but that is alarming. But, another thing that's kept me up at night, and this has even made me nervous before we had our last global pandemic, and maybe this is more of a problem in the Arctic as well, where it's closer to human civilization, but I've read some papers where scientists are looking to see what organisms are frozen in the ice and then could sort of come back to life, as it were, or come back into contact with our human civilizations, and there might even be a concern that they could be pathogenic. So I'm wondering if any of your research touches on that aspect, or if there's any organisms that we're discovering trapped in the Antarctic permafrost or if you think that's something that could be an issue of concern in the Antarctic.
Thankfully, there's very little that's pathogenic or dangerous in Antarctica. Actually, I always joke that it completely ruins me as a field scientist because there's no rattlesnakes, there's no, dangerous organisms to speak of, at least inland. On the coast, there's seals and orcas and things, which you should keep an eye out for. But yeah, mostly the pathogens coming out of permafrost are in the Arctic. It's sort of mostly in Siberia where this is happening. And in Antarctica, the organisms that live there are so cold adapted and really have no adaptations from a warmer, more pleasant time that they're not particularly pathogenic. They're not dangerous to humans.
Okay, good news. I also wanted to ask you because we just had an episode a couple weeks ago on ice cores, and we learned all about how they serve as a climate record since, I guess, as far back as we're able to reach the ice. I'm wondering what historical records are frozen in the permafrost and how they can be information that's useful for us today.
Permafrost holds a lot of interesting climate data, but it's not in the way you would think of with an ice core. So an ice core, snow piles up and that gives you change over time and with the gases that are trapped or dust. In Antarctica, the permafrost doesn't pile up like that. So you have to kind of look someplace else. Instead, what the permafrost really does is it acts like glue. And it's kind of like, there's people who super glue together their Lego creations when they're done with them. It really locks them into place. So you get this wonderful record of landscapes that in other parts of the world would have blown away or been washed away by streams. And they're still there in Antarctica and they're in pristine condition. So one thing we can do with permafrost, for example, is go and walk around Taylor Valley, one of the big dry valleys. And right now it's this big open alpine valley. It just kind of looks like you're walking through, Utah in winter. And as you walk up the desert valley walls, there's these river delta deposits. So places where, a stream entered a lake and dumped a whole bunch of sediment and it looks like a fan. And there's no stream there now in many cases. And there's certainly no big body of water that it flowed into. So it's like, what's going on with these deltas that are struck to the walls? And what's going on with the deltas is they're a paleoclimate record. So they're telling us that at some point in the past, and we can tell when in the past because we can radiocarbon date algal mats and microbial mats that are trapped in the deltas. The Taylor Valley was filled up with water. So how do you fill up this desert valley with water? Well, you stick a cork in the end. So during the last ice age, when the ice sheets grew, they actually expanded and flooded up into the dry valleys and closed up the mouth of the valley. They melted, and as the local glaciers melted in summer, it produced this giant lake, kind of like the paleo lakes in the desert southwest of the U.S. So during the last ice age, places that didn't have standing bodies of water did. So the deltas were deposited in that, and then as the ice sheets retreated, water level dropped. So the deltas got dropped sequentially lower and lower down the valley walls. And then they're locked in place by the permafrost, by this super glue. So now they're there, 20,000 years later, and we can actually go and date them and figure out how quickly ice sheets retreat in Antarctica, or how quickly they retreated during the last ice age, by looking at these permafrost deposits and dating them. So they're landscape clues that tell you something has changed, and they're beautifully preserved by the permafrost. So when you put those two together, you have a record of climate change in those dry valleys, which is really better than almost anywhere else. That doesn't have ice cores. I'm a little jealous of the ice core people.
Okay, that's fascinating. So the ice cores have a record of how the climate changes over time, and the permafrost record has a record of how the Earth changes. So if you cross-reference those data sets, you can get an understanding of how the Earth responds to changes in climate. That's so smart. Wow. I'm curious, one thing I read when I was reviewing your work was that one concern with permafrost thaw is that some data that you were just mentioning will be lost, right? Will no longer be available to us. So how much of a concern is that? And what questions might we not be able to get the answers to if the data in that permafrost gets melted away?
Yeah, so the permafrost holds the landscape together and it preserves the deposits. And so if you thaw a paleo lake delta, for example, that's been held together by ice for 20,000 years, it just turns into mud. And then all of the datable material in it, those algal mats that you're radiocarbon dating, trying to figure out how old it was, get all mixed together, they get destroyed. And so the real game now is trying to figure out, what do we still need to know? So there are many, for example, paleo lake deltas that haven't been dated in the dry valleys. They're telling us something about the rise and fall of the lakes. And that's telling us about the ice sheets waxing and waning. And again, if we're interested in how quickly ice sheets can vanish, for example, because of climate change, we should look at the most recent time ice sheets were much bigger and how quickly they vanished to their present state. And that information is in these coastal Antarctic deposits. So we need to find those. We need to figure out which ones are most likely to thaw first. And that's really the ones closest to the coastline where it's warmest. It's the ones at the lowest elevations. It's just like in temperate environments, that's the warmest spot. And so those are the ones that are going to be turning into mud. There's also the search for the oldest ice, right? If we have not just the last ice age, but if we have multiple ice ages or really kind of historic moments in Earth history, 10 million years ago, we want to capture what's preserved in those landscapes before they thaw too, because that's really a once in a lifetime, once in a species kind of opportunity.
Wow, once in a species. And it seems like the Cold Dirt Lab has a lot of work to do really quickly. So for anyone interested in soil, it looks like there's a need for you to become an Antarctic soil scientist quickly. I think we're going to take a hard left in the interest of time because there's one thing left that I really want to talk about with you today, which is outer space. I saw a bit of your research touches on Mars. Can you tell us about how all of this ice frozen kilometers underneath Antarctica has to do with outer space?
So I actually got into Antarctica because of Mars. I was a planetary geology PhD student, and my advisor had an opportunity to come collaborate with an Antarctican, and I came along and I've been doing it ever since. But the reason that folks who are interested in Mars want to go to Antarctica is it really is the most Mars-like place on Earth. It is the coldest, driest desert on the planet. A cold day in Antarctica, like minus 50 Celsius, is sort of an average day on Mars. It's as close as you can get to the red planet without having a hellacious commute. The other thing that makes it really similar is that it's really dry. It is the driest desert on Earth. And so when you put these two together, there are landforms that exist in only sort of two places that I know of in the solar system. And one is the dry valleys in Antarctica, and the other is Mars. And so as we begin getting more information about Mars, particularly from satellites that are taking high resolution images of the ground, particularly Mars's polar regions, we start seeing these landforms that look just like permafrost features in Antarctica. And why should people care about that? Well, the permafrost features in Antarctica have ice in them, right? They're made out of ice and soil and salt. And so that means that the Martian features are very likely made out of ice and soil too. And so if you're in the business of wanting to establish a city on Mars or even just a base on Mars, it's much easier to bring just the tools that you need to generate water than to bring a whole, community's worth of water with you. It's much too heavy. So if you can take that ice on Mars and melt it and capture it, then there's your city's water supply. So that now is in ice, and that ice is in Martian permafrost.
Then, if I'm understanding, I guess all the insights that we have from studying the permafrost and the soil in Antarctica can help us form hypotheses about Mars and maybe give us an understanding of what we might expect.
Exactly, yeah. So Antarctica is very much the training ground for developing ideas about Mars. It's where our predictions come from, and then we send a spacecraft to figure it out and test those. And when we send the spacecraft, whether they're landers that scrape away the dirt or radars that can kind of shine through the sediment, what they keep finding is sort of between 30 degrees latitude, sort of temperate latitudes on the Earth, and the pole, Mars has a thick pasted on deposit of ice. It's like cream cheese on a bagel. And it seems to have been deposited sometime in the last few million years. So it's very young. It's trying to work its way back to the poles. That's, that Mars has ice caps just like Earth. And that's where the ice is stable. So this is Martian climate change. In the last 2 to 4 million years, the polar ice was destabilized on Mars. It deposited at lower latitudes, and now it's working its way back.
Wow. Okay. Martian climate change is another word that I have heard for the first time in those last however long we've been speaking. My next question is, because we had an episode where I spoke to an astrophysicist about research that he does out of Antarctica, and I was asking him, why do we care, right? Why are we doing this type of research? And the answer was basically just for the sake of better understanding the universe, which we hold space for that on this podcast, and I think it's super cool. But I just want to ask you about applying the research on Mars using these Antarctic insights, because I was not expecting to hear that we're already at the stage where we're looking for water sources for a potential society. But what sorts of applied research is coming out of this space?
You might be surprised to hear it, but I mean, a lot of people are interested in humans on Mars. NASA has plans to send humans to Mars in small numbers. Elon Musk and SpaceX have plans for large numbers. And so, permafrost on Earth is not a growth industry, right? It's thawing. But permafrost on Mars really is and permafrost geomorphology is the key to unlocking where these deposits of ice are. And so there have been several meetings and workshops, sort of landing site selection workshops, where a bunch of us Mars permafrost geomorphology types, Mars radar scientists all sit together and try and figure out where is the ice, and in particular, where is it accessible, right? So there's plenty of ice, but the further towards the poles you get, the colder it gets. So you want something that's closer to the equator. It also makes it a lot easier to land. It also makes it a lot warmer. But the warmer it gets, the less stable the ice is, so the deeper it goes underground. So we're kind of in this ice prospecting business. So the pure science, like Martian climate change, is really informing what could be the nuts and bolts of future human plumbing. It's the most important resource for space exploration.
Wow, I was not expecting that. But I guess here we are today, 2024, and this is what we're talking about. I think I've taken a lot of your time today, and I think we've covered quite a lot of topics. The last question I have for you is, where can people find you and follow your work?
I tweet from time to time at Cold Dirt on what is now X, I guess. I occasionally tell some science stories at thescua.org. But mostly I publish a lot of what I write with my students. And so if anyone needs to find some polar science and they don't have access to it, shoot me an email, and I'm always happy to talk about it and to share research results.
Okay, perfect. I will make sure to include links to all of the above in the episode description so that people can find it easily. And this is the part where I say thank you so much for coming on the show today. Thank you for teaching us about cold dirt and also for your very important research in this space.
Oh, no worries. Thanks for getting in touch. This was tons of fun. I'm, like you said, a giant polar dirt nerd, and so I'm always happy to talk about it.
You've been listening to South Pole. You can find more information about this week's guest and links to their work in the episode description. Cover art for the show was done by Laura Wong, and the music you're listening to was done by Neela Ruiz. I am your host, Clark Marchese, and this episode was produced and engineered by me. So if you found it interesting, send it to someone you know. South Pole is part of a larger network of sciencey podcasts called Pine Forest Media. We've got one on plastic, one on drinking water, and a couple new ones coming out soon. You can find more information about us in the episode description or on our website at pineforestpods.com. We're also on TikTok and Instagram at Pine Forest Media. And if you love the show and want to support science communication like this, a 5-star rating across platforms and a review on Apple Podcasts is one of the best things you can do to help science reach more people and for the entire network to grow. All right, thank you so much to all of you who have made it this far, and we'll chat soon.